Okay. One more example in this topic to talk about. We'll harken back to something we saw back in chapter 1. So this is an interesting one, I think. So here we have a problem that says, Here we go. Evaluate the power of the complex number. Now, when you look at this, right, this is example number 2 of DeMoivre's theorem. But DeMoivre's theorem, like we said, is very specific to polar forms of complex numbers. When you have any complex number z, okay, that is written in polar form with a modulus and an argument, then we have this format for calculating that. This number, clearly not in polar form, okay? Now, before we go any further, just want to reiterate that I could have given you this problem back in December when we were talking about sequences and series. In that chapter, we covered something called the Binomial Theorem. So if you recall, I mean, this would have been really heinous of me to do, but there's a way to expand this where we're doing 7 choose 0, right? And then 2 to the 7th power, and then 2i to the 0 power, right? We subtract these numbers and that goes here. We take whatever, we subtract these numbers and that goes here, and then this number goes there, right? 7 minus 0, 7, and then this bottom number in what we call the binomial coefficient goes here, and then we add to that, we do 7 choose 1, and then we subtract those, and that number goes as this exponent, and then we have 2i raised to the first dot. This can be done, right? So let's be clear that you wouldn't need DeMoivre's theorem to do this. But if you want to use DeMoivre's theorem to do this, you need to convert your number into polar form to start, which we had at this point had quite a bit of practice in. I always prefer to have a picture drawn, right? So if we move over 2 and up 2, so this is 2 and this is 2, technically this is 2i, right? We need to know the modulus and we need to know the argument. Now, if we say this is a distance, I'm saying it's 2i, but really in terms of real number distance, we can call that 2. So we don't need to do any formulas for this if you're really in tune with what's going on, and I'm going to use that shortcut. This right here is an isosceles right triangle, so I know that theta is 45 degrees, okay, 2 and 2. And since it's a 45, 45, 90 triangle, and this is 2 and this is 2, I know that the hypotenuse is going to be 2 radical 2. That's our modulus, right? The absolute value of this number, its distance from 0 is 2 radical 2. So, in other words, if I reformat the way this problem's written, it's really 2 radical 2 times the cosine of 45 plus I times the sine of 45. And this whole thing is being raised to the 7th power, right? So all I'm doing is rewriting the standard form into polar form. And to do this, I take 2 radical 2 and I raise it to the 7th power. And then in here, I take the arguments and I multiply them each by 7. This is according to DeMoivre's theorem. Now, we'll talk about this piece in it. Well, we can talk about that piece first, I suppose. When I do 2 radical 2 to the 7th power, there's a whole bunch of different ways we could talk about it. I'm going to jump over here for this. So this is some work I'm doing in the margin. If we're in pre-calc honors, we could plug this into the calculator, right? But any odd power of an even radical is not going to work out into an integer. We'll say that again. Like when we take the square root of 2 and we square it, we get 2, right? When we take the square root of 2 and we raise it to the 3rd power, that's the square root of 2 times the square root of 2, which is 2, times the square root of 2, which has a radical 2, right? So we still get radicals when we raise something like this to an odd power. So let's hash this thing out over here, right? This will be fun. A nice review of our exponents. So this is 2 radical 2 to the 7th power. we can, quote unquote, distribute exponents into products. So this is the same as 2 to, come on now, work with me, 2 to the 7th times radical 2 to the 7th power. 2 to the 7th power, I believe, is 128. Ooh, let me check that. Pretty sure. 2 to the 7th power? Anybody? Waiting. 2. $128. Yeah, I was right. Okay. So, and then we also have here radical 2 to the 7th power. We could like draw 7 of these out if you want, right? 1, 2, 3, dot, 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 dot. Let's get cheeky with it. This is really 2 to the 1/2 power raised to the 7th power, which is 2 to the 7/2 power. I've still got this 128 over here. I haven't lost that yet, but 2 to the 1/2 power raised to the 7th power. Exponents of exponents get multiplied. So we're doing really 7 over 2. Now, 7 over 2, and I realize this may be getting a little too technical, is really 3.5. So this is 2 to the 3rd power times 2 to the 1/2 power. Because 3.5, I could add 1/2 to 3 to make up this number. So we really get 128 times 8 times radical 2. And then when we do this, we get 1024 radical 2 from that. Okay, there's a bunch of other ways. You could have done this, right? Let's go back. I suppose maybe this would be simpler. If I had 7 of these, 1, 2, 3, 4, 5, 6, 7, every 2 is equal to 2. That's equal to 2 times 2 times 2. That's our 2 cubed. And then we have this one left over, right? What I was saying here is that 7/2 as a mixed number or a mixed fraction is 3.5. And which is the same as 3 plus 1/2, which I could decompose into this product. So if that's too much of a stretch, sorry, but I thought it would be kind of fun. So we get 1024 for that product. Now here we get the cosine of, let's see, what is this, 315, I believe, plus I times the sine of 315. And these are numbers once again. So in polar form, we'd be done because 315 is between 0 and 360. Okay. If they want standard form, so you can check this off. Say polar form, here it is. This didn't specify, but it was given in standard form. So I'm going to write this in standard form at the end. The cosine of 315 is in quadrant 4. Cosines there are positive. So we get radical 2 over 2 plus I. The sine of 315 is in quadrant 4 where sine values are negative. So this is negative radical 2 over 2. There was a time earlier in the semester where I said, your understanding of the unit circle will determine your success or failure. This is because of problems like this. If you're still trying to figure out what's 315 again, it's in quadrant 2, or excuse me, it's in quadrant 4, and it has a 45-degree reference angle. So the sine is radical 2 over 2, but because it's in quadrant 4, the sine values are negative. So we have 1024 radical 2 over 2 plus negative 1024 radical 2 over 2, and these can be reduced to 512 plus negative 512 radical 2. I believe that's right. My math should be good there. So we get this. Oh, what I forget? Forgot the I. Where am I going to put it? I'm going to have to wedge it in here. We'll put it right here. Okay. I can put it at the end as long as it doesn't go underneath that radical, but that's good. Okay.